I am DK Panda from the Ohio State University, and my colleague Professor Subramoni is also here. So two of us will be taking you through this tutorial. The title is High Performance and Smart Networking Technologies for HPC and AI. The slides are available here. Please take a look. You can download, um, and might be hurry, you can post it also, the
Sure.
link
Sure.
on the web. Um, so the outline will be like this. We'll have introduction, just a very high level introduction, followed by just asking questions why we are talking about high performance networking for HPC and AI. Go through a little bit of like a past history, what has happened, and why networking like InfiniBand, high-speed Ethernet, Rocky, Slingshot, all these are coming into important focus these days. And then we'll go into more details. We'll start with the communication model and semantics of high performance networks. And then after that, we'll start with InfiniBand and high-speed Ethernet. That is the kind of a common networking technologies used on many systems. We'll start with those. And then gradually we'll compare and contrast with Omnipath, NB-Link, AMD Infinite Fabric, Amazon EFA, then Slingshot. Then we'll be going into a little bit about the smart NIC, which are more like the DPUs, IPUs, and what can be done there. And then we'll come back and take a look at some dedicated AI chips like Cerebras, Havana Gaudi. Uh, and once we get exposed to all these features, we'll try to also take a look at the software stacks, like how exactly these hardware features, the networking features are being linked to the upper level softwares. And then we'll take a look at some sample case studies and performance numbers, and then we'll conclude. And please feel free to ask questions on the chat. Hari, you can monitor, and then um, we can answer. So if you take a very broad look, over the last like 20, 30 years, there is a lot of growth in high performance computing. And that growth is happening in terms of processor performance, especially chip density is doubling almost every 18 months. We see more and more number of cores per socket. So each socket or each server is also getting these days very heavy. Like the latest AMD, if you take a look, it has like 128 cores. Similarly, Intel has 96 cores. So within a node, of course, there are intra-node interconnects, but here we'll be focusing more on the across the node or inter-node. So when these nodes are becoming very dense, so there is a need, you also need to have good inter-node connectivity so that they can get balanced out. And this is where I think the commodity clusters are becoming very important. And a lot of people have been using those commodity clusters all over the place. So when I say commodity cluster, the idea is that can you actually go and then purchase a bunch of CPUs, GPUs, interconnects, memory, storage, and then have some like open source stacks or any other libraries is available, and then you have the complete system. So that's what we'll be keeping a view here. Um, so if you take a look at this top 500 list, which is like a commodity computing clusters, uh, where they fit in the top 500. Many of you must be knowing about this top 500. Um, this actually evaluates the ranked systems, supercomputers in the world twice a year, one in November in US and once in June, July, May, June, July in Europe. So if you take a look at the history, in the very early days, these systems used to be very proprietary systems. Okay. Like these, think of like these are like the connection machines, IBM, um, um, traditional systems, IBM Blue Gene and all. So that means you purchase those systems entirety. Okay. So you cannot just go and buy pieces of the hardware and then put it together. But over the years, as the commodity networking has come, now you can see almost like a very close to 100%. Most of the systems are commodity in nature. Okay, that's what you will see. And then what is happening? It is not just the compute cluster is a like we are focusing on the computation here, but you will also see storage clusters. They also have the similar trend, like you have a bunch of servers, metadata nodes, compute nodes, server nodes. You are connecting them with some network. You also see this is the most dominant one, for all the e-commerce, financial, all the transactions, like all the think of like Amazon and all. So these are the data centers where you have like a different tiers, tier one, tier two, tier three kind of thing, and they are also connected with switch. So if you take a look at the kind of the role of networking is very diverse here within the system, across also the systems, LAN and WAN. And at the same time, we'll also seeing cloud computing is also getting a very broad view. Um, all high performance networking technologies are gradually moving into cloud computing. In fact, if you take a look at the like kind of the Azure, their high end cluster instances just exactly use InfiniBand. Similarly, the Oracle uses Rocky. AWS, we'll talk a little bit about later. It actually uses their own proprietary adapter called EFA, but that also gets interconnected with Wi-Fi. So there also the networking technologies are getting importance there. And of course, these days we are in the field of AI. So all the deep learning, machine learning, as you would have been hearing, all these large scale trainings, you need like thousands of GPUs uh, for several months to get the training done. And especially the large language models, um, as you can see here, is becoming larger and larger. Um, and continuously people are trying to make it larger, and that means the training requires very large systems. And when you have large systems, the role of networking is also becoming very important. And this also gives a very quick overview of how we have moved in the field of like AI, starting from 94 million to here like a 540 billion parameters people are talking. And already there are like a trillion parameter consortium. There is an organization looking at to train these trillion parameter models. So if you take a look at this very broad perspective saying, what are the networking and IO requirements? Okay, so if you're an architect, you're trying to ask the question, and here what you will see that there are multiple parameters. Of course, in the traditional way, always people want the latency and bandwidth. Latency is like a round trip or a one-way latency. You can think of a server to server. And we also want to minimize this. And the bandwidth is like a from node to node at the rate at which we can transfer. Now, in addition to these two parameters, another parameter has become very important over the years is called CPU utilization. And this CPU utilization is not for application, but for protocol processing. Okay. So if you have a network, we have some protocols. So the question is, how much time does it take for the protocol processing? So if I have two technologies, networking technologies, they deliver similar latency and bandwidth, but one has a lower CPU utilization, that means that is better. Okay. If instead of like spending 30% of the cycles for network protocol processing, if I can spend 10%, then my 90% of the cycles are left for application. Okay. And that we'll see gradually as we go along, that will play a very important role in all these networks. So that is kind of the basic performance. Then, of course, we need good storage area network, good wide area network connectivity, quality of service, reliability, availability, serviceability. So all these are important for production-based systems. But then the question is like everybody wants it with the low cost. So this is where a lot of competition happens across different vendors to reduce the cost of the system. So let's take a look at with this, again, very high level perspective. Let's take a look at some basic computer architecture and see what has happened over the years. Okay. So if you take a look at, I'm sure in any of your like a digital logic class, you would have seen like we have a processors with some cores, memories, then there is an IO bus, then there is a network adapter, then it gets connected to the network switch. So this is a typical server architecture. Now, what happens over the years when you are putting it together, a system with some kind of processor, some kind of memory, some kind of a network, you will see that there could be different kinds of bottlenecks. So one could be processing bottlenecks. So these processing bottlenecks is what we are talking here is protocol processing bottlenecks, okay, not the actual application. There could be IO interface bottlenecks for the rate at which data in and out can go. And the third one is network bottlenecks. So even though we have very good systems, might be the overall network has an issue. So let's take a look at these three bottlenecks in detail. So protocol processing bottlenecks, if you start like a I'm sure all of
Yeah.
you are familiar with TCP/IP, UDP/IP. These have been there since the evolution of the computer networking. And the standard TCP/IP stack actually goes through a lot of these multiple layers. And here you will see like a host processor handles all aspects of communication, like data buffering, integrity, routing aspects, signaling. So once you go through all those steps, it takes a lot of time. And that's why if you do some TCP/IP level communication, it'll be little bit time consuming. Like in the best systems these days, you may see like a 3 microsecond, 5 microsecond, depending on the system and the processor speed. Now the question is, can we really reduce that? And this is where we'll try to introduce some kind of a user level protocol in the next section, and that will try to reduce the latency in a significant manner. So that is the protocol processing bottleneck. Now let's take a look at the IO interface bottleneck. So if you take a look at the server, so this is the IO interface, which actually determines the rate at which data can come inside the server and outside. So, and sometimes is also known as the last mile bottleneck. So if you take a look at the history, like a PCI started in 1990, and that is the IO interface used to be there. And it used to be like a bus, and it has 33 megahertz, 32 bits. So it was a 32 bits, and each bit was like 33 megahertz. So if you do a math, it was like trying to deliver 1 gigabits per second bidirectional. But then, of course, as the technology improved, that was not sufficient. So PCI X was introduced. They expanded like 32 bits to 64 bits, and also 33 megahertz. They went to 133, and sometimes some versions also had 266, 533 megahertz. Okay. So the broad idea was that we can increase the clock speed and increase the bus width, and then performance will keep on increasing. But if you take a look, if you remember like your basic digital logic class or any analog logic design class, when you have a lot of bus, like a bus, and then each bit is operating at a very high rate, you will see a lot of crosstalks. And then with those crosstalks, your error keeps on increasing. And that's what people found out when in the late, like in 1990, people thought that well, this will not be the technology to move forward, and we'll see a solution a little bit later to address that. And the final bottleneck is actual network bottleneck. So that means we have designed the servers very well, even with the network adapter. But once it goes to the network, whatever happens with the network, the congestion, the bandwidth, those things matter the performance. So this is where Ethernet, if you remember, like started in 1979. It was for almost 14 years. That was good enough. But then as computers became faster and faster, people introduced fast Ethernet, gigabit Ethernet, ATM. MIRINET was the first technology, which was actually the cluster technology. It was a wormhole routed system, which came around 1 gigabit per second, and then the fiber channel came. So, so all these were like, as you can see here from this list, like we're in the mid 90s, and then people saw that we need a better solution. And this is where the InfiniBand and all high performance networking came into the picture. And InfiniBand and high speed Ethernets were introduced in the market around 2000. Since InfiniBand was new, it actually aimed to address all the bottlenecks like processing, protocol processing, IO bus, network speed. And then Ethernet actually was already there, and it aimed to directly handle the network speed bottleneck and relied on complementary technologies to alleviate protocol processing and IO bottlenecks. So we'll take a look at these in a little bit more details. Any questions so far? Please feel free to post it in the chat.
There are no questions on the chat or on Slack.
Okay, okay. Thank you. So let's continue. So then what we'll try to take a look, let's start with the very high level introduction of InfiniBand. And it started actually as a consortium. Some of them, these companies don't exist, like a Compaq, Dell, HP, IBM, Intel, Microsoft, and so on. But if you take a look at their goal, it was to design a scalable and high performance communication and IO architecture by taking an integrated view of computing, networking, and storage technology. So it was not just networking. It was a networking component and the architecture, but they were trying to take a global look at how the systems need to get designed. And then the volume one version was and actually introduced almost like 24 years back, October 2000. And then as the technology got adopted, by system. Uh, um, Many organizations, system sizes kept on growing. Um, People discovered limitations. Okay, in the InfiniBand architecture, people found some limitations, and this is where several annexes were released after that, like RDMA-CM, ISER, XRC, Rocky, virtualization. So like this, the specification also has kept on getting updated. So the very latest one you will see like a 1.7. We'll talk a little bit about that. That was released last July. So you can actually go to this InfiniBand Trade Association website and actually download. Okay. But if you download the document, you will see that it's not a simple like a flyer. It is a 1700 pages document. Okay, because it's a very open specification. Anybody can design these kind of systems. Of course, I mean we don't have to understand all the things unless you are trying to actually design components like the adapters, switches, cables, all those details are there. Here we'll try to take a look at a little bit at a high level from a more from an user perspective or an architect perspective. And depending on the need, you can always jump in and then go into more details of the architecture. So similarly, just like InfiniBand started in the 2000, um, prior to this, Ethernet was there. That was like a 1 gig alliance. So then the 10 gig alliance was formed. And here the idea was very similar, just like InfiniBand, to achieve a scalable and high performance communication architecture while maintaining backward compatibility with Ethernet. But then as Ethernet evolved, multiple issues were discovered. Okay, so the first thing was like a, if you remember the Ethernet starting from like a 10 megabits, 100 megabits, 1 gigabits, 10 gigabits, everything was going in as a factor of 10. So after 10 gigabits, obvious choice is to go for 100 gigabits. But then the 100 gigabits, if you try to put in a system, you remember we discussed about these three bottlenecks. The IO interface bottleneck became very apparent in the sense, unless technology is there to handle that IO interface, you cannot actually have, even though you have the network as 100 gigabits per second, you cannot actually communicate with the server. So this is what happened over the years as InfiniBand technology was evolving. It actually came to like a QDR technology we'll introduce very soon, quad data rate. And by that time, actually the interface technology, IO interface technology has evolved so that at least some intermediate like a 40 gigabit Ethernet can be introduced. Okay. So that's what Ethernet Consortium, Ethernet Alliance had a lot of discussion. So instead of jumping from like a 10 gigi to 100 gigi, there is an intermediate technology was introduced called 40 gigi. We'll see. And that was very similar to InfiniBand QDR. So then as the technology again evolved, we'll see that the Ethernet, and then we'll introduce very soon PCI Express. So that PCI, what we introduced earlier, got moved to PCI Express. And that PCI Express also we'll see will have some concepts of lanes. So people wanted to reuse technologies from InfiniBand to even to Ethernet, okay, at the hardware layer. So this is where over the years you will see now we have very different kind of a range of Ethernet products with different kinds of cost performance, 25 gigi, 50 gigi, 100, of course, it is going to 200, 400 kind of things. And and this is what I introduced, like the 40 gigabits of was introduced with an IEEE standard. Then 25 gigi was introduced. And of course, new concepts like energy efficiency, power consciousness, they have also been introduced in the Ethernet. So now let's take a look at how at least these two technologies, InfiniBand and high-speed Ethernet, they are trying to handle those three bottlenecks. Okay. So once we know that, then later on we'll see other technologies like a Omnipath, Omnipath Express, Slingshot. Everybody is exactly handling the same thing. So we don't have to repeat all those things. We'll just take a look at the features. So the basic network speed bottleneck, if you don't know, like this InfiniBand, the word actually stands for infinite bandwidth. Okay. And of course, you can ask a question. I mean, what does it mean by infinite bandwidth? There is nothing like that. But that's how it was coined in the sense that as the technology will, as the computing technology, storage technologies will keep on improving, InfiniBand will continue to grow. That was the idea of that infinite bandwidth. Okay. So what the basic idea was that if you remember, like we had the PCI, what is a bus-based systems, and it has 2 degrees of freedom, like the bus speed and then the number of bits. They changed that to similar kind of like a 2 degrees of freedom, but in a little bit different manner. Instead of a bus, it was changed to a bit serial differential signaling. Okay, so it was an independent pair of wires to transmit independent data, and in the information literature, it's called a lane. So you can think of like an independent pair. They are actually twisted and covered, and then you can have any number of lanes to put a bigger cable. Okay, so it still has 2 degrees of freedom. Okay, so you can change the clock speed of the lane, and you can have more number of lanes. And if you play properly, we'll see in the next slide, the bandwidth will keep on improving, and that's what exactly has happened over the years. So theoretically, there is no perceived limit on the bandwidth here. So so let's see how it has actually played out over the years. So here you will see like these are the technology we talked. So InfiniBand started here. I'm saying 2001. It was introduced in 2000, but the actual technology adapters and all commercially it got available in 2001. So what they started in the beginning, it's called single lane 1x, and the rate, the lane was characterized as SDR, called single data rate. So that means if you take a look at the clock, we're able to send 1 bit in that clock. So that's what is known as one SDR. And also in the networking technology, there is a, some of you might be familiar, there is a payload rate and actually the physical rate. Okay. And and most of the time at the network layer, we do some kind of error correction, encoding, decoding. So there is some overhead. So what InfiniBand introduced, so what we are trying to show here is the actually payload rate. Okay. The actual SDR, if you look at the literature, it is 2.5 gigabits per second, but it was using 8 to 10 encoding to take care of all those error corrections and all. So the payload rate is 2 gigabits per second. And similarly, Ethernet was also introduced at the same time. The payload was 10 gigabits per second, but it was using 8 to 10. So actually the physical layer was 12.5. Okay. So then what happened in 2 years, the InfiniBand consortium wanted to move into higher bandwidth. So they kept the same SDR, but they changed the lanes. You can see from 1x to 4x. So that means instead of one lane, it is a 4 lane. So their 4 lanes are put together. You get it in a single cable. So then you can see the bandwidth improved from 2 to 8. So then in another 2 years, it actually moved to DDR, called double data rate. So that means in the same clock cycle, we're sending 1 bit. Now, instead of that, we can send actually one on the rising edge, one on the falling edge. So it will be the double data rate. And then the number of lanes remained the same 4x. So it became 16 gigabits per second. And at the same time, actually, you see that this is a kind of a time frame 2005. IBM actually was a part of the InfiniBand consortium. They actually went ahead and they had a SDR technologies, but they had 12 such lanes. So if you put it together, 24 gigabits per second. This was quite high bandwidth in the 2005 timeframe. Okay, so there were some systems were deployed using that technologies, but what happened, since there were like a 12 such lanes, the cables were very heavy, and that actually led to not very stability if you in the integration. Okay, if you think of like servers, you plug a network card like this or network card like this. These cables were heavy, so that they were bending the network, so the system was not being reliable. So over the years, actually, that technology didn't succeed. But then what it moved ahead was that the same 4 lanes in 2007, this was QDR. That means quad data rate. I referred to this earlier, like a 4 bits you can actually send in a clock. So that's how it became like 32 gigabits per second. And since that IO interface was already providing that 32 gigabits per second, then the Ethernet consortium I was mentioning earlier, instead of from 10 going to directly to 100, they had the intermediate one, which is the 40 gigabits per second. So then in another 4 years, InfiniBand moved to, this is a little bit of interesting dynamics. What happened typically, in the digital world, we go in a multiple of like 2, 2, 4, 8, 16 kind of things. So here, what happened instead of QDR, like going to 8 bits or 16 bits, they had some intermediate one called 14 data rate. Okay, so that's how this FDR is introduced. And interestingly, what happened by that time also the encoding technology also improved. So here they were using 8 to 10 encoding, but then the encoding community came up with better solutions which can do um, 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 60 to uh, 60, 64 to 66 bits. Okay, kind of an encoding they came. So it's only with a very little overhead you should be able to do this encoding. So if you do a little bit of math, this is where in 2011 with 14 data rate it was able to Infinimon was able to deliver like a 54.6. And then if you have two such lanes, many of these network adapters have like a two ports out. If you do some channel bonding here, or later on we'll introduce a terminology called multi-port. If you do that, then in 2012, Infinimon actually introduced like saying we can actually deliver 100 gigabits per second. Okay, that was the first time. 2012, it went to a little bit ahead of 100 gigabits per second. But then what happened? Since these components people wanted to reuse. Okay, in the cables, in terms of adapter, the interfaces, the even the like encoding chips and different chips. So they wanted to leverage like the single lane concept, and that went back to either you use one lane or two lane. This is where 25 or 50 gigabit was introduced. Okay. Once again, 10 gigabit was there, Ethernet 100, then 40 was introduced. Then if you use like a one such lanes or two such lanes, you can have 25 or 50. These were the intermediate technologies were introduced. And then in, of course, 100 gigabits was also available. Then OmniPath, we'll talk about that a little bit later. That was also like an InfiniBand technology, but instead of an offloading, it tried to use onloading. We'll come to that concept a little bit later, and that also got introduced as 100 gigabits per second. Then we had InfiniBand going into what they call it like a EDR, enhanced data rate, still using 4 lanes. They came to 100 gigabits per second. 2017 was HDR, high data rate, to 200. And then the slingshot was introduced from Cray, that is a 200 gigabits per second. Omnipath Express was introduced. It is basically built on Omnipath, but it was a little bit of variation. We'll talk about that. That was 100 gig. Google also came up with its own network, but it has been, I don't think it is being deployed anymore. That was like 100 gigabits. And then InfiniBand 2022, it was like the next data rate they introduced, the same 4 lanes, but with 400 gigahertz per second. So this shows actually playing with those two dimensions, like the number of lanes, you can actually keep on moving. And then just if you take a very quick look, like starting from 2001 to 2024, the network speed has doubled 200 times. Okay. So that's what is actually a biggest improvement has happened in the field, and that leads to a lot of excitement, and a lot of the systems are being developed. And later on we'll see like the GPUs and all, these are all very network hungry. And now we are trying to design these kind of systems, uh, still not very balanced. People still need more and more networking demand. And we'll see this is where the InfiniBand and high-speed Ethernet, in fact, have started already talking about 800 gigahertz per second, 1600 gigahertz per second, and etc. Okay. Any quick questions here? Is this concept clear? I think people can post it on the chat.
Yep. Currently, there are no questions on the chat or Slack. I
Okay.
think we can proceed.
Okay. So then let's take a look at the protocol processing bottleneck. So you remember I introduced like TCP/IP, and TCP/IP said if it goes through the standard like the layers, it has a lot of overhead. So these concepts started. The research actually happened in almost the mid 90s. Okay, so the idea was that how we can reduce that latency in it in the concepts of like intelligent network interface cards. Okay, we started with this adjective intelligent. In fact, in the modern days, we'll see things are becoming much more intelligent, and this is where the smart NICs are coming into the picture. We have a section, we'll go over that. So the idea is that can we offload protocol processing to the adapter instead of the adapter just being dumb and moving packets? Can it actually do some protocol processing? And the idea is very similar. What you can see, what we do in the real world. If some of you are executives and managers, I'm sure you have assistants and secretaries to help you. So if you take a look at that executive assistant model, bring it to the real systems here, we can think of our executives could be like CPUs or GPUs, and the network card can be your assistant or secretary. Okay. So then the question is, okay, how do I move just like in the real world, you tell your assistant saying, yeah, set up this call or may send this email to 100 people or handle this event, all those kind of things you can offload so that you are free as an executive to actually take care of high level decisions. Similar designs are coming within the software stack. We'll introduce like MPI and all. You can actually um, have this kind of newer paradigms so that the processor actually doesn't spend a lot of time on protocol processing. Okay, it actually offloads to the network adapter, and the network adapter can actually take care of this. But then to achieve this, there has to be newer kinds of APIs or newer kinds of interface, and that's what in the literature, in the networking literature, if you go and search, it stands for user level communication capability. Okay. We'll go into a little bit more detail saying how that API looks, how actually it gets offloaded into the network. But the idea is that if you do that, then you don't have to go through this software signaling between communication layer as TCP/IP had introduced earlier. These layers can be implemented by dedicated hardware units or some shared host CPU. There are multiple architectures can come. So then the final thing is the IO interface bottleneck. Go ahead. Somebody is asking. No. Okay. So let's take a look at the interface with IO technology. So if you remember, the InfiniBand started in the beginning. So when we say data movement, typically it is from, you can say from the server I showed in the picture, but typically it comes from the memory of the sender, goes through the network, over the network, the other adapter, and to the memory of the receiver. So in the originally when InfiniBand introduced this lane technologies and all, they wanted to actually have their adapters directly talk to the memory. Okay. And this was like a early 2000. Um, Now, if you see Intel at that time or any, mostly the Intel were developing all the server platforms. So even though Intel was a part of the InfiniBand consortium, they had their own, like the front side bus, all those internal architectures, and they didn't want to make it open. Okay, so that led actually to some controversy in the community. If you go back and look at some of the websites, you will see that in fact in the around 2005, 2006, there were some time when Intel declared actually they are withdrawing from InfiniBand consortium. Also, Microsoft also announced that they are withdrawing, but then that didn't, but that was not good for the end users. Okay, and at the same time, another thing was happening, the evolution of the GPU technology. Okay. It was not only networking, the GPU technology was also evolving. If you look at the history of NVIDIA and all, you will see it started as a graphics engine just for our like a rendering visualization. But over a period of time, they came up with this CUDA. So that was introduced as a computing engine. But then if you take a look at the GPUs are also attached to the server through an IO interface, PCI, or in the modern day is a PCI Express. So unless that IO interface is much more matured, you cannot actually move data between host memory and GPU memory. And that is also crucial. The GPU, even though it has a lot of computing power, unless you load it with the data, you cannot operate. So then what was happening is, even though Intel was not very happy to allow InfiniBand to enter into the IO interface area, it was also getting a lot of pressure from the GPU vendors, um, at least NVIDIA at that time, saying there is a bottleneck. So then what happened, in this is like a typical silicon area, silicon Bay Area concept. Companies, you compete with each other. If you cannot compete, you just join. Okay, so that's what exactly happened. So that PCI technology got moved to PCI Express. Okay, I'll show that in the next slide. And then once that PCI Express came, in fact, here if you see, they exactly adopted the same concept of the lanes. Whatever InfiniBand was proposing from adapter to adapter, now they extended that to the interface side, both on the sender and both the receiver. So you can actually see again, either it is a 1 lane, 2 lanes, 4 lanes, 8 lanes, 16 lanes, then that will lead to, it's a like a giga transfer per second. So this is where the PCI Express got born. Okay. And as of now, if you go most of the systems, okay, we'll see some changes happening again. Both InfiniBand and high-speed Ethernet today come as network adapters that plug into the existing IO technology. So that IO interface bottleneck issue is a little bit resolved up to a certain extent. Okay. But then what happened, even though PCI Express, because PCI Express there is a consortium, then of course InfiniBand consortium is there, and these people are deploying the systems. So sometimes PCI Express consortium was not moving very fast. Okay. And that's what happened. If you remember a few years back, the number one system at Oak Ridge National Lab was Summit system. And so there they wanted to use the GPUs, multiple GPUs for node, and with a very good high interface, like a high-speed network, but also having a good interface with the with the memory system. And PCI Express was not able to deliver that. And this is where actually the whole idea of this will see later on NV-Link or NVIDIA Link was introduced. Even though NVIDIA was a GPU company, but they saw that there is a limit, so they introduced their own networking technology called NV-Link, and the Summit system was actually a collaboration between NVIDIA, Mellanox, and IBM. IBM also allowed the interface to be updated to a higher speed so that that system could be deployed. Okay, and 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 based on that, similar like a competing technology is also introduced. Like there was a cache coherent interconnect for accelerator, CCIX, CAPI, Open CAPI, then HP introduced this Gen G. So a lot of these IO interface architectures again got evolved. They compete with each other. But then over the years, what has happened again, all of them have not survived, but then they have again got rearranged into this new thing called Compute Express Link or CXL. I think some of you might be familiar with this. So this is what is getting momentum now. Open industry standard. It provides a cascaded interconnect between CPUs, accelerator, IO devices, various flavors of the memories, and it also allows like a currently if you see like a most of the servers like a typically you go 96 or 128 cores, and within that you can do shared memory, but outside of that you cannot do. You have to go through MPI or some PGAS, and this is where all the InfiniBand, Slingshot, high-speed Ethernet comes. So CXL is trying to expand that up to certain extent. Okay, like you cannot connect CXL with sorry, you cannot connect like let's say 10,000 nodes with 10,000 servers to SAXL, but you can go up to let's say 8 or 16, depending on the technologies and the switches, so that within that, like a super node or a super server, you can actually have shared memory. Okay, and that improves significantly performance, programmability, etc. And this is where I think the CXL technology has been evolving. If you take a look at the CXL 1.0, 1.1 up to 3.1, that is the very latest standard. And many companies in the Bay Area are actually working on some of these products. And there are also a lot of simulators available. So hopefully we'll see a lot of traction on this technology in the coming years. Hope that gives a very high level perspective of all these bottlenecks and all. Any questions?
No questions in chat or Slack.
Okay, thank you. Yeah, please feel free to ask questions so that as we instead of just talking, we can also have more discussion. So this is at a let's say lower level. So now let's see how do we build the system. Okay. So when you build a system, when you're talking really like you're running an application, let's say think of like a training or inferencing or even a scientific workload, you are running on 1,000 node with 400 GPUs and all. There has to be some kind of a communication stack, so through which you activate all these underlying technologies. So this section, what we'll try to do is we'll take a look at that communication model. okay, and the semantics, which actually bridges the features of high performance network with that of the upper layers. So what we'll introduce over the years, we'll give a summary here. Broadly, there are two kinds of communication model. One is called two-sided and the other one is called one-sided. We'll take a look. So let's start with the two-sided communication model. So the two-sided communication model, basically you can think of like our emails. Okay. So let's say I send you an email. I am sending you an email, but the total control of the receive lies with you. Okay. Like from my mailbox, I can just send a send, but unless you log on to your system or your mailbox, you don't receive my email. Okay. And after you log on and after you detect my email, the control also lies with you what you do with that email, whether you store or forward or delete, entire control lies with you. That's what is called two-sided. So this is also what we'll see here. Let's say in the MPI, those of you are familiar, like MPI send, MPI receive, there are different kinds of primitives, but you will see that this is the basic two-sided operations. And and to if you remember, like these days, of course, the technology has changed. If some of you are familiar, like 10 years back or 15 years back, um, I cannot even, mailboxes were so small in size, you cannot send a big message. Okay. It actually says that, yeah, the receiver mailbox is full. I cannot receive. So most of the time, to get performance, of course, you need bigger mailbox. The same idea also gets used in the high performance network. So that means if I want performance, let's say these are the three nodes like a P1, P2, P3, they have their SCAs. We'll call these are like a network adapter. We are using InfiniBand terminology here, which is called host channel adapter. So most of the time, if I want to get very good performance and somebody is designing the high level like a network and protocols, you typically do something called a post receive buffer. Okay, so that means the receiver is ready. So then what happens most of the time in a HPC community, the communication happens with polling. Okay, so there is a difference between polling and interrupt. Some of you must be knowing. Polling means I'm continuously polling. In this case, P2 is waiting for a message to arrive. It will keep on polling. Let's say it expects from messages from P1 and P3. It posts to receive buffers and keeps on polling. Okay. So in an MPI world, if you're familiar, you can say MPI receive, 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 or an I receive actually in this case. Uh, and then what happens, the sender side, when it computes, and then when it comes to ready to send the message, it sends a post send. Okay. So then you will see, look at the animation here, the message will actually go over the network, go to the adapter. We'll discuss later on the topology and all those stacks. But as soon as the message reaches there, since P2 is polling, that adapter is polling, it will get the message and then will give it to the P2. Similar things will happen if P1 sends a message, you will get it, P2 will get. So this is what is called two-sided. So that means from the sender side, I'm just sending the message with a destination address. Okay, destination server address or a process address or a core address, we'll see. But there is another improved model which is called one-sided communication model. Okay, so one-sided is more like a trusted communication model. So what does that mean? That means if you remember like a real world, let's say you have a very trusted colleague, so you can always say to your colleague saying, look, when my door is open, you can always come, take a book from my office or open the file cabinet, take things or put back things. Okay. And this is what is one-sided. So that is much more better because if my friend is coming to take a things from my office, he or she doesn't have to interrupt me. Okay. And that is the whole idea of this one-sided communication model. So typically in the many of the programs, you do some kind of a init. And during that stage, you have a global region creation, buffer infos are exchanged. Um, and then what happens, you will see now, let's say I am sending the P2 wants to send a message to P3. You look at the animation. So as soon as actually it gets written, the data goes over the network and this actually adapter knows where to place the data. Okay. We'll see that a little bit later with a better animation. So in this case, actually the sender has to have the actual destination memory address in the packet. Okay. So that it goes and gets written. And then similar kind of things here you can see. P1 also can do uh, the written. I believe there's some chat, something has been posted. Hari, can you see what are the? I got
Yes,
some pop-ups. Yeah.
yes. I just got it too. So the question is this: at very large scale for strong scaling case of either HPC or AI training, do you see the actual need for high bandwidth per port? I believe that as you scale your application, your bandwidth requirements per port would go down. This would be counterintuitive with respect to small scale single box where scale up communication is substantially higher and proportional to HBM bandwidth. So
There are
basically, the
multiple.
question is this:
Yeah, go ahead.
do you need high bandwidth as you scale out to many number of nodes?
Yes, yes. The answer is actually yes. You need. So what is happening if you see the modern way the people are deploying, the single node doesn't have only one GPU. These are like you get currently like you can go up to 4 GPUs, 8 GPUs kind of things. So in that context, what is happening is in fact sometimes the network is not balanced actually. So with 8 GPUs working together, when you are trying to do the training and especially sending very large messages from each GPUs, you want to do the STD, the reduction, or it's an all-to-all or all gather. There's a big demand for the bandwidth, and unless you have that kind of a bandwidth, you will be effectively actually taking more time on that training, and then in that context, your strong scaling applications will get affected. Okay. So in fact, there is another direction will not talk here today. Uh, exactly for that reason, in fact, not only in our group, other groups are working on some on-the-fly compression technologies. We can discuss it offline. So the idea is that since there is a big demand and these big messages are going, and if the network bandwidth is not enough, it's like you can think of multiple islands are being connected together. So you can use actually compression technologies to reduce that message so that you get a good balance of your computation and networking. Okay. Any other question?
No, nothing, Dr.
Okay.
Murali.
So let's then move very quickly. We'll try to finish this and move to the next thing. So how does this exactly happens then? I mean, all these one-sided communication, two-sided communication, posting buffers. So in all these high-speed network, there's something called a memory registration. That means before we do any communication, all memory must be for communication must be registered. Okay, because typically a program is written with a virtual address, but like the actual physical at a DMA and all happens in the physical address. So these are the kind of the steps. So in the beginning, you when you send a virtual address saying, okay, I want to send this message. Okay, you are not actually sending the message at that time, but you have the intent. So you send your virtual address and length. The kernel actually does the virtual to physical mapping. Okay, this is very important because we want security and all those kind of features. And once it does that virtual to physical address translation, it actually the adapters have intelligence, even the basic adapters. This SCA or adapter caches the virtual to physical mapping. Okay, so it has actually just like processor cache, all these adapters have cache. So it puts that virtual to physical address mapping there and gives two keys. One is called a local key, that is for your own local one, and the R key if it wants somebody else to write to you. And once you have this process done, and most of the time this is done in the initialization so that you are not affecting the actual communication, but sometimes you can also do on demand. The performance will get affected a little bit, but that also gives flexibility so that you can register more and more memory. So once you do that, when you actually send your message, in addition to the actual data, you send it something, this key called a L key or the local key. And this is, you will see interestingly. So this time when I'm trying to do the communication, it doesn't touch the kernel at all. And that is the very big difference between like these all high speed networks and let's say traditional TCP/IP stack. Okay, because traditional TCP/IP with the multiple layers, you have to invoke the kernels multiple times. So here, since the directly at a, this is what is known called kernel bypass protocols or OS bypass protocols or user level protocols. There are a lot of terminologies here. Then the adapter actually validates that L key, saying it has come from the right process, so that to it provides some kind of security here. And then if somebody else is trying to do a remote um, write to me or remote read from me, I have to give that remote key to somebody else. Okay. It's just like think of your office. If you want a trusted person to open your door, let's say you have some like a instead of a actual key, if you have some, the coded one. So then you say, oh, my code is 345. Okay, the person comes, then puts that in, and then can enter your door. Same thing happens like a you send that key to remote, and then when the remote person is trying to do this RDMA operation, in addition to the data, it has to provide that R key. And in the beginning, the basic InfiniBand standard, actually this R key is not encrypted. Okay. So the assumption is that okay, if the system is within a data center or within a building, those are enough protected so that people cannot come and then touch it. But then InfiniBand has also grown into like a wide area network technologies, even across continents and all. So in those cases, you need to encrypt it. And then there are routers. Those are very little bit expensive, but those routers actually do on the fly, like a real time encoding and decoding or encryption. They do it. So now let's try to put all these ideas together. These are like a nice set of three animation slides. It will actually help you to understand the protocol. So let's start with the two-sided model. So what we are showing you, this is like a sender, this is the receiver. These are the processors. This is your instrument device. This is the memory. So internally, just like you think of that executive assistant or a assistant and secretary, most of the time, there is something called a like a outgoing box or incoming box. So here we'll have a send QP or a receive QP. And then there will be another box called a completion queue, like an event which gets completed. So here we'll have both the things on sender side, receiver side. So in the beginning, as we said, there will be a receive will get posted. So it's called receive UKI. In the InfiniBand terminologies, different networks have a little bit of variation of the names. So write queue element or called as UKI. And that has information saying, okay, if a message comes from this person, where to put it. Okay. Typically an executive might be telling the secretary saying, yeah, I'm waiting for this call or for this email. If it comes, forward to somebody or give it to me, interrupt me. So that's what we are trying to do here. So the receiver is getting ready. Then the sender does a similar things when it is ready to send the data. It sends also a wookie. And in this case, it is a two-sided. It has information, excuse me, on where to take the data. And once these things are posted, you will see the processors or the executives don't have to be involved in the actual communication. So that's what we'll see. So this wookie gets picked up by the adapter, and then it actually goes and grabs the data from the memory, puts them into appropriate packets and all those things, sends, and it goes over the network and it reaches the adapter of the receiver. But interestingly, since it is a two-sided, something has to be done here because this message cannot move from the adapter to the memory. So this is where what is going to happen. There is a matching will happen. Okay. Because that receive buffer might be this adapter is getting message from processor 1, 2, 3. It needs to know where to put them. So there will be a matching will happen here. And once it knows where it needs to be placed, it goes and places the things there. And then what happens, like some kind of a completion entry is added into the completion queue. Then it sends a hardware ACK. The sender also puts a completion queue on the sender. So the whole operation is over. So both the executives can actually, there are again a mechanism. You can have either the executive can come and do a polling, or it can have interrupt. So now if you see this protocol, so you'll see that the processors are involved only on either side, like either a posting receive key or post sending key and pulling out completion key. Okay. There is no involvement. The processors are actually not sending the data. And this is where, if you remember, I introduced CPU utilization for protocol processing. That is where this concept comes in. So if you can offload these to the adapters, then your CPU utilization goes down. So in the modern InfiniBand adapter, it will be seeing very low, like even a 5%, 3%, depending on your message sizes and all. Okay. So that means most of your cycles are left for your computation. So that is the two-sided. So now let's see how the one-sided will work. So as you said, as we discussed, one-sided is a little bit more advanced. So here what happens, the receiver doesn't have to post anything. Okay. The sender posts the wiki, but this wiki contains not only information about the data location in the sender, but also the receiver buffer. Okay, where exactly it needs to be fetched. So this is like a trusted friend returning your book, opening the door, and then sending, putting the book on your bookcase, and that's what we'll see here. The animation, it gets the data, and see, it directly goes and then places the data in the memory. And then if there is a hardware act gets sent, there is a completion entry comes. So then, of course, the question is, okay, how does this processor knows that the message has arrived? So there are multiple techniques. Um, Either you can there are some strict ordering. Some adapters provide strict ordering. InfiniBand actually does that. So if you have send a message and if the receiver knows that I can actually wait for the very last byte of the message, okay, then I know that the message has arrived. Or you send the first the RDMA message, like in this case a push, send a follow-up message, okay, saying that it got done. That can be a two-sided. Or sometimes even in the message itself, you can actually encode some bits saying that the message has delivered. So there are all these different trade-offs are there. So here you will see that the initiator processor is involved only to posting the send key, pulling out the completion cookies, and there is no involvement from the target process. So if you design your upper level software and middleware appropriately, you will see that receiver can be continuously, you can actually get a very good overlap between your computation and communication. And that's what happens in the modern day MPI libraries, machine learning libraries, all these, the middleware people have been continuously enhancing these so that they want the network overhead to go down and down and to have the maximum overlap with your computation. The same thing also InfiniBand introduced something called atomics. Those of you are familiar, atomics are like like a fetch and add, compare and swap. These are very much needed for distributed systems. And here you will see, let's take a look at the fetch and add. So that means I have some data and the receiver has some data. If I have 5, receiver has 10, this needs to be added, and then 15 goes back to both of them. Okay, both memory, but we need to do it in an atomic manner. And that's what happens. The InfiniBand provides this. So here you will see like a 64-bit segment. It goes there and then it actually fetches from the memory. It performs the operation. So this was the very early days when InfiniBand actually introduced computation to the adapter also, not just communication, but computation. Later on, we'll see over the years, like a in-network computing has come. The adapters have become more smart, like the DPUs, IPUs. So these days, actually, you can even do computation in the adapter, computation in the switches. And based on the system, based on your target application, you can actually try to balance these. When I say computation, these are computations related to communication. Okay, most of the time, not the user level computation people have not uploaded. We have done a little bit of research on that to put it into the DPUs. You will see some examples later on, but this is where the field is moving. So once the operation happens here and here, you finish. Okay. So here again, here you will see that this kind of operations, initiator processor is only involved in the post send key, pulling out the completion cookie. There is no involvement from the target processor, so that we can also have a good overlap in for the atomic operations with the computation. So those are the point to point, but there is also a very big need for collectives. And this is needed in the HPC as well as in the AI, and especially AI, all this training. A lot of collective operations get done, like a broadcast, scatter, gather, reduction. We'll see some examples later on. But think of like these collective communications are designed through some algorithms, and the algorithms are a collection of point-to-point steps. Okay. So we saw some examples of the point-to-point earlier, two-sided, one-sided. So those can be actually used here to even design better and better collective algorithms. So with this, we'll we'll put a pause here and let's see if anybody has any questions. Then we'll go down. Um, so we have got the concepts like from 100,000 feet level, we have come to like, let's say 40,000 feet. Now we'll go down even to the 20,000 and 10,000 feet.
Dr. Panda,
Any
can you
question?
stop screen share so that I can start?
Yeah, I'll stop. Uh, um, okay.
Thank you.
There's a question here. I think.
Where?
Yeah. No. I think published studies showing large scale thousands bandwidth utilization justify. So I think this is from Joshua. I think
Yeah.
Joshua. I think in some papers they are there. I need to exactly take a look.
So one example could be the recent work by Microsoft for their like zero architecture when they are trying to train 16K context length LLMs. They do have fairly large message sizes even at multi-thousand GPU scale. So let me take search for that and I can post it on Slack a little later.
I just want to comment that these large models, even if you have large messages, because the job it's between tens of thousands of GPUs, what you actually end up sending to each of those GPUs is actually in the sub megabyte. Therefore, your effective bandwidth per pair of GPUs goes down. So the question was related with bandwidth per GPU going down or bandwidth per port, associating one port per GPU going down as you scale up.
Okay. We can try to share some studies along the direction. Thank you, Joshua. So again, folks, feel free to uh, mention your questions. It'll be fun for us. So now we are going down a little bit and looking into the architectural overview of various high-performance networks. So again, each one of these networks have standards and specifications which are over 1,000 pages long. We are trying to compress that into like maybe 4 or 5 slides. So there will be significant, let's say, filtration and drop of information that is happening. So I think that's the nature of the tutorial. So we'll start with InfiniBand high-speed Ethernet and see how they are converging to start with. So let's try to compare your traditional ISO OSI software stack, which has application layer, transport layer, network layer, so on and so forth, with the IB or InfiniBand stack. So if you look at the physical layer, one of the major differences is that InfiniBand does not have wireless. So it does have copper or optical, similar to traditional Ethernet. Between the physical and link layers, you have the network management tool called OpenSM. So OpenSM or Open Subnet Manager is responsible for bringing together the entire network, making sure that there is no deadlock, the routing tables and the switching tables are configured correctly. It also helps with configuring InfiniBand features like multicast, and flow control and error detection also happens at this level. Now, if you move up one step, you have routing. Although typically most IB networks are not routed, but products for routing do exist in the community, and there are various vendors who are offering such products. The major differences between the traditional Ethernet and IB happens at the transport layer. With Ethernet, the interface has always historically been the sockets interface. So you have open, read, write, close, so on and so forth. And one of the major differences here is that with the sockets interface, you have to, you had to go from the user space to the kernel space, and there was a cost associated with that, which was not suitable for high performance networks. That is what the Open Fabric's verbs interface tried to avoid. So you don't have the context switch from the user space to the kernel space in the critical path. You are able to do that once at init and then avoid going through the kernel for most of the communications. Just like Ethernet has TCP and UDP, reliable and unreliable, the Open Fabric's verbs or IB side also has RC, which is reliable, and UD, which is unreliable. And on top of this, you will have applications written using the Open Fabric's verbs interface going over the IB stack. So having said this, let us see how your transport stack looks like. Okay, so you can have applications or middleware written for sockets or verbs. Again, this is going back maybe 10, 20 years in history. So if you are using sockets, you would be using TCP/IP or UDP, and you could go through the Ethernet driver, Ethernet adapter, and Ethernet switch. When InfiniBand came into the ecosystem, obviously they want to play well with the sockets interface. So that is where the first kind of convergence happened. So if you had an application who were willing to go straight over IB verbs, you could do that. But if not, you also had a bridge protocol called IP over IB, where you would encapsulate IP packets into IB frames and send them over an InfiniBand adapter and an IB switch. So when this came out, your Ethernet was still at the 1 gig or 10 gig level, and IP over IB could give you a bandwidth boost over your traditional network. So that is one way where the first convergence happened. Now let's look at how the evolution of IB has been happening over the last couple of decades. So we started with SDR, or single data rate, a long time ago. So then we went through various evolutions, and right now we are at NDR, 400 to 800 gigabits per second. And your typical deployment scenarios is with 4 pairs of twisted wires. So that is what is represented by 4x. So as was mentioned earlier, you potentially can have any type of bandwidth as your wires get thicker, but your typical deployment scenarios is 4x. And currently we are at the NDR regime. There are a lot of deployments with EDR, HDR already out there, and NDR is what is currently the state of the art. So recently, IB had released the 1.7 volume, and the biggest changes there were support for large radix switches. Basically, this will reduce the overall number of networking hardware you will need to deploy like a larger scale cluster. Your previous radices were about 32, 48, or 64 ports, which would require a lot more network hardware. But with a large radix switch, you will need significantly lesser. And there are other enhancements done to the standard with the 1.7 release as well. Let us look at some of the architecture and basic hardware components. So there are multiple components. So your network adapters are called channel adapters. You could have a host channel adapter or a target channel adapter, and an HCA for short. Each can have multiple end ports. And to have support for quality of service or differentiated quality of service, you have what is called as virtual lanes or VLs for each port. And you have the software endpoints are called Q pairs, just like you have sockets on the Ethernet side. You have Q pairs as a software endpoints that allows the application to interact with the network adapter. You also have switches and routers, and like switches are for obviously intra-domain, and routers are for inter-domain. You also have links and repeaters to extend the range. A long time ago, Intel had come up with copper to optical conversion at very, very, very low latencies, as low as 550 picoseconds. And this had allowed the InfiniBand networks to span longer distances. This was done almost like 20 years ago. So let's go forward and look at how the hardware protocol offload happens. Again, we are trying to compress multiple chapters of a large specification down. So we are trying to pick and choose what we think is interesting and useful. So this is how your IB stack looks like: the transport layer, network layer, link, and the physical layers. So we'll start with basic IB communication semantics. So as I mentioned, the software endpoint is called a Q pair. So it has a pair of queues, a send queue and a receive queue. And you will post metadata regarding what you need to send, or from where you need to send and to where you need to receive, into work queue elements or wookies into the send queue and the receive queue. Once the network adapter has processed these wookies, they would be placed into a completion queue or C queue as completion queue elements or cookies. So this is your basic operation. So suppose I want to send 64 bytes from a particular memory location. Then first I would do a registration, as we saw earlier. Then we will create a work queue element saying that, okay, this is the address from which I want to send. This is the number of bytes. This is the key. The IB device will get that metadata, fetch the data from memory using DMA engines, send it out through the network, and then post the send book key into the completion queue, indicating to the process that the operation has been complete and the buffer is safe for reuse. So let's see how hardware, so you have complete hardware implementations of all of this in various vendors. So we'll see how the network and link layer operates. So there are lots of capabilities here, but we'll just focus on a few like buffering and flow control, virtual lanes, and quality of service, and switching and multicast. So if you look at virtual lanes, it is very important. The concept of virtual lanes, although we are describing it in a bit more detail for IB, the same concepts do exist for other high-performance networks like Omnipath, OPX, Slingshot, EFA, everything, okay? So you have two concepts, virtual lanes at the hardware level, as we saw earlier. So virtual lanes give like reserved buffering at the hardware level to send out packets, and this will avoid head-of-line blocking. At the software level, you have various service levels that the network administrator or the system administrator will set up, and these would be exposed to end users. There will be a service level to virtual lane mapping table, which maps various service levels to underlying virtual lanes so that they go through different virtual lanes, avoiding head-of-line blocking. Now, there is, how do you give differentiating priorities to the virtual lanes? There is something called the virtual lane arbitration or VLARB table, which determines how many flips you need to send out from one particular virtual lane before moving to the other. So with a combination of different virtual lanes, the service level to virtual lane mapping table, and the virtual lane arbitration table, we can implement differentiated quality of service for an IB network. The only thing is that every single IB device should be configured exactly the same. So that is why the OpenSM or the Open Subnet Manager is tasked with the responsibility of doing this so that the entire subnet looks the same as far as differentiated quality of service goes. And please note that the same concepts do apply for almost all other high-performance networks. So let's now move into layer 2 routing or switching. So just like on the Ethernet side, you have MAC addresses, you have what is called as local identifiers or LIDs on the IB side for intra-domain switching. For multicast packets, we have what is called as multicast group identifiers or NGIDs. And these IDs tell the switch through what all end ports or egress ports the packets needs to be replicated out through. And you have separate interfaces for multicast group management like create, join, leave, prune.
I gotta go, so I'll see you tonight.
Okay. So you have multicast group as well. Let's take a quick look at how the switch looks like. So the basic unit of switching is what we call as a crossbar. So this is fully non-blocking, very highly provisioned. So this is also called as a pizza box switch, basically because the switch kind of looks like a pizza box. Okay. So unfortunately, these are extremely expensive to implement when you go to very large scales. So your typical larger scale switches that you see in markets, your director class switches with 300, 500, 600 ports are collections of crossbars within a single cabinet. And these are what we call as non-blocking switches. So for a crossbar, imagine that you have a system where every house is connected to every other house with a separate road. So there will be no congestion whatsoever, but it'll be damn expensive to implement and it'll take a lot of real estate. Your non-blocking switch is like our typical road system where if you have multiple cars going in the same time, there's probably not a lot of congestion, but you could potentially create a scenario where there's congestion on the node. Okay. Now, having mentioned congestion, let's take a simple example of how IB switching or routing happens. Suppose you have a two-level fat tree like this. You have the leaf blocks and the spine blocks. You have process 1 on node 1 and process 2 on node 2. And let's assume that node 2 has two destination addresses or LIDs, 2 and 4. Okay. Now let's see what happens when node 1 wants to, or process 1 on node 1 wants to send a packet out. Let's first look at the forwarding table on this particular leaf switch. So the forwarding table says that if your destination LID is 2, you go through port 1. If it is 4, 4, you go through port 4. Okay. Let's assume P1 sends a message with DLID of 2. That will go to this particular spine switch, come down and reach P2. Now, suppose that this particular spine switch is down or these links are congested. At that point in time, if we have multiple LIDs, we have the flexibility to send a packet to P2 using a different LID, which will take a different route through the network. So by having multiple LIDs, you can have redundant paths as well as avoid hotspots in the network. So this was done a long time ago when the IB networks were still statically routed. Nowadays, you have dynamic routing capability in the network. So this is kind of becoming less and less useful as we go forward. But still, there are not many vendors who have been successfully able to bring this in. But this is just there so that you know why you could have multiple LIDs in the network, so that you have different routing algorithms. Now let's take a quick example of how IB multicast works. So typically, the subnet manager entity can run on an end node or a switch, depending on the choice of the system administrator. The first time a process wants to join a multicast group, it sends a multicast join to the subnet manager, who then sets up the multicast group by configuring the switches appropriately. The next time somebody else wants to join, a similar step happens. And if you look at the switch in between, you will see that multiple egress ports have been tagged with this multicast group ID. So at a later point in time, if any node wants to send or any node which is part of this multicast group wants to send a message out to this multicast group, the switches will replicate the packet, and the end node will only have to send one copy instead of multiple copies. So this was an initial hardware offload solution, network hardware offload solution that InfiniBand has. Recently, there are other more advanced network offload solutions. So with IB multicast, you could only replicate packets. You could not do higher value operations like mathematical operations. So this is where the newer support called SHARP, or Scalable Hierarchical Aggregation Protocol from NVIDIA Mellanox, comes into picture. So here what we do is, you have the ability to collect data from the end compute nodes, send them to the switches, do the mathematical operations in the switches in a hierarchical fashion, all the way up to the root of this tree that the job created, send the result out through the switches back down to the processes, so that the number of hops required to finish the compute operation and the communication operation will be significantly lower. And this, as we will see later on, leads to excellent scalability as you go to very large number of nodes. A lot of communication libraries like the MWAPIC MPI library, as well as Nickel, the NVIDIA Collective Communication Library, has inbuilt support for these kind of hardware-enabled collectives, both the multicast and SHARP. So let's finally look at the transport layer. So on the Ethernet side, you only have like a reliable connection and unreliable datagram, but IB has a rich variety of protocols. Each has a different equation in terms of scalability and performance. So RC is full feature rich, but it has a significantly high connection overhead. So if you have M processes and N nodes, we have a very high overhead to establish all-to-all connectivity. UD, on the other hand, has a fixed overhead, but it does not have any of the cool features like RDMA or atomics that we talked about earlier. So vendors have tried to come up with intermediate protocols with the features of RC and the scalability of UD. So these are called extended reliable connection and dynamic connected, as you can see here. So they have all the features of RC, while maintaining the scalability of UD. So this is what we have on the host side. But about 10 years ago, GPUs came into the picture, and various vendors wanted to come up with solutions to send data and receive data from directly GPU buffers. So this was where GPU Direct RDMA came. And back in 2011, our group, NVIDIA, and Mellanox had worked together to come up with this a seminal paper back in the International Supercomputing Conference on how you can pass GPU buffers directly into a communication runtime, make the communication runtime aware of GPU buffers, and send the data directly from GPU buffer on one node to GPU buffer on a different node, leading to high performance and high productivity. This was the first such GPU-aware communication runtime in the community. Right now, if you look at it, there are lots of similar solutions from each GPU vendor. So NVIDIA has Nickel, AMD has Rickle, Intel has Sickle, so on and so forth. And Habana, which is an AI vendor, has Hickle. So everybody has their own GPU-aware communication runtime. But we in our group had come up with this feature back in 2011, first for the NVIDIA plus Mellanox ecosystem. As a result, we were able to significantly reduce the latencies and improve the bandwidth for communication. Now let's look at a few bridge protocols. So just like we mentioned IP over IB, there were other protocols that people tried to come up with because you had the requirement for staying on with the sockets API, but improving the bandwidth. So IP over IB was the initial model where you would go fully through the kernel. So you had this like a slightly improved performance, but the bandwidth still wasn't that high because you weren't able to use all the hardware offload capabilities. Again, remember, this is rewinding the clock almost 20 years. You should not compare this with what currently Ethernet is able to do. So back then, people came up with what is called as a sockets direct protocol, which will do kernel bypass RDMA semantics, and this primarily targeted the large message spectrum. So the small message latency was still not great because you had to go over the user to kernel interface, but the large message bandwidth was significantly improved compared to IP over IB. Now, in order to address the small message performance while retaining the socket semantics, some folks had introduced what is called as R sockets. So this intercepts the sockets calls and makes it go over RDMA CM. And this gives you good bandwidth and good latency. But unfortunately, because of the limitations of the sockets interface, you still cannot do RDMA or atomics directly from the application level. So with the advent of these two, this is how our protocol stack looks like. So initially, if you remember, we started with TCP/IP and RDMA at both ends of the spectrum. And vendors had introduced IP over IB. Later on, SDP and R sockets came. So this is, let's say, in a naive fashion, this is how they would relatively be placed in the overall spectrum of sockets versus verbs. So going forward, let's quickly look at the high-speed Ethernet family with the IVAR protocol. So this is when the Ethernet consortium and the Ethernet vendors began to realize that, oh, okay, this is a good InfiniBand or verbs is a good protocol. Let's see if we can move this protocol over our regular Ethernet networks. Okay, this is a comparison of how IB compares with IVARP and high-speed Ethernet. So some of the benefits of high-speed Ethernet is that you could have out-of-order data placement. You could also have fine-grained and dynamic rate control, a lot of improved quality of service support, all the very nice network management features and ACLs of Ethernet immediately became applicable here. So with the advent of IVAR, two more verticals came here. So you could go through the sockets interface, TCP/IP, and you could have hardware offload capabilities, where you could offload segmentation, reassembly, checksum, all of those things in hardware, and a bunch of others as well, and go over your traditional Ethernet network. Or you could go over IB verbs, again, TCP/IP at the user space, go through an IVAR adapter, and go through an Ethernet switch. So the benefit here is that you get improved performance but you can go over the Ethernet network fabric. The next level of convergence that happened was RDMA over Converged Enhanced Ethernet, or RoCE. Okay. Sorry, I think there was a question. My apologies, I didn't notice that. So the question is, with same AI algorithms and hardware infrastructure, different parallelisms to map to GPU clusters, do you see huge difference on network traffic characteristics and demands? So I think I'll get back to that. I don't get that question fully. I'll get back to that a little later. So with RDMA or Converged Enhanced Ethernet, RoCE, the benefit is that you are able to make your IB packets go over Ethernet networks either at the L2 level or at the L2 and L3 levels over regular Ethernet networks by changing the last one or two layers of your protocol of your packet. With RoCE, the InfiniBand link layer would be changed to an Ethernet link layer so that now it is switchable. With RoCE v2, the link and the network layers would be changed so that it is switchable and routable. Thus, RoCE v2 brings all the benefits of your like your traditional Ethernet network management infrastructure, including ACLs, snooping, network monitoring tools, etc. And consequently, your management stack now, looks like this. Okay. So this is your full featured management stack. So you have RSockets here, SDP here, and you have RoCE that will come here. The next high performance interconnect that we have is Omnipath. So Omnipath has a fairly long history. It started off at as path scale, then QLogic bought it, which was later acquired by Intel, and recently have been spun off into a different company called Cornelis Networks, and they have rebranded it as Omnipath Express. So the Omnipath fabric looks very similar to IB, but it is an enhanced version of it, has more features. It has support for higher number of fabric addresses. It has also support for larger number of virtual lanes, while InfiniBand specification only supports 16 virtual lanes. The Omnipath specification supports up to 32 virtual lanes, but the basic process of providing differentiated quality of service is similar. And with the advent of the Omnipath network, we have a new higher level interface called OFI, or Open Fabrics Interface. And we have a different underlying communication protocol as well. Now, this slide is a feature comparison of all the different networks that we talked about: IB, IVAR, RoCE, RoCE v2, and Omnipath. So these two slides are your cheat sheets to see how your InfiniBand Ethernet Omnipath has evolved in terms of hardware and software over the last couple of decades, and trying to decipher all the different terminologies that vendors may post you. So slides number 80 and 81 gives you a quick high-level overview of all of these. Now, these are more recent advances. With the advent of higher performance GPUs, various GPU vendors felt that the PCI bus was not catching up quickly enough. PCI was stuck at PCI Gen 3 for a very, very long time, but the bandwidth requirements of the GPUs were growing much higher than how the PCI was evolving. So the vendors came up with their own network interconnects, and the first one of these is from NVIDIA called NVLink and NVLink 2. You have NVLink, different generations of it with different capabilities, and each generation is made available with different classes of their GPU. So with the latest Grace Hopper GPUs, you have the 5th generation of NVLinks available with significantly higher network bandwidth capabilities. So are there plans to provide network computing on RoCE-based networks like SHARP on Ethernet network? Mellanox, NVIDIA is heading in that direction for providing support, better support for Ethernet, but we have not heard anything along that direction concretely. But they are looking into Ethernet-based networks, that much we know.
Hari, just might be we can add at least, I believe some other vendors like Broadcom and all, they are working on in network computing for their adapters, but I don't think they are publicly available yet.
Yes, that is also right. So what Dr. Panda mentioned right now about Broadcom is along the ultra Ethernet side. So there are different vendors trying to come up with solutions for Ethernet. We hope that, and we are working with several of these vendors as well from the Ohio State group. We hope some of these solutions will be productized and made available to the public soon. So the NV links can be connected in different kind of topologies, either a switch topology or a simple point-to-point communication topology. So this is a slide showing your switch topology, where you can connect multiple GPUs to an NV switch. And this gives you significantly high intra-baseboard and inter-baseboard communication. And once this kind of solutions are made available, you also need software capability to go over these. So as I mentioned, we were one of the first in the community to come up with GPU-aware communications. Since then, various vendors have come up with extremely optimized solutions for GPU-based communication. Nickel or NVIDIA's collective communication library is one such solution. Although the name is Collective Communication Library, nowadays they have support for all sorts of collectives as well as point-to-point operations. And these give you excellent scalability and performance for single node as well as multi-node NVIDIA plus IB enabled systems. And this kind of shows how your large language models scale with Nickel on modern NVIDIA DGX GPU systems. So just like NVIDIA came up with NVLink, AMD also came up with their own version of intra-node communication fabric to interconnect their CPUs and GPUs called the AMD Infinity Fabric. So you have like a die-to-die interconnect on the CPUs as well as CPU to GPUs. So this gives you significantly high bandwidth to the memory as well as between CPUs and GPUs. And they have designed, just like NVIDIA designed their collective communication library, AMD also have designed their own ROCm collective communication library, and it is pronounced as RICL. So it is very similar to Nickel in terms of APIs and functionalities, and it gives you extremely good communication performance for intranode and internode point-to-point and collective communication mechanisms on small as well as large like AMD-enabled systems. So Frontier is a good example where RICL gives you very good communication performance. So Frontier is a top supercomputing system at the Oak Ridge National Labs. So far, we have looked at solutions for GPU-based fabrics and let's say commodity fabrics. Now, Amazon also has been working on the interconnect area for a long time now. So they started with the C1 adapter, which was at 1 Gbps. So most recently, they have gone to the third generation of their elastic fabric adapters with a bandwidth of 200 Gbps and a latency of very close to 6.5 microseconds, which have a lot of optimizations. Now, you might think that, hey, 6.5 microseconds, that's very bad. People are talking about 1 microsecond and things like that. So this is not something that was introduced by mistake. This is by design. From Amazon's point of view, they wanted the HPC systems to be very well integrated with their existing e-commerce and large data centers. So equal cost multipathing was very important for them to make sure that by introducing HPC into the large-scale fabric, you don't screw up the existing communication traffic. So in order to ensure this, they spray the packets over multiple paths over the network, and they also combine the packets unbeknown to the user at the receive side using a newer transport protocol called Scalable Reliable Datagram, or SRD. And it is because of these that the latency is slightly higher than your typical latencies that you would expect with high performance interconnects. So with the advent of the new scalable reliable datagram or SRD protocol, this is how your transport protocol slide, which we looked at maybe 10 or 15 slides before, looks like. So with SRD, your communication overhead is very similar to the dynamic connected on the IB side, and you have the same capabilities that RC provides. So this is uh, what we have with regard to the Amazon's EFA adapter. Let's quickly look at Cray's Slingshot network as well. So if you look at Slingshot from Cray HPE, their biggest selling point is that they have excellent QoS and congestion control and very low jitter. So this was their main focus, as described by Steve Scott in the 2019 keynote at the Exacom workshop. So Slingshot, apart from all the other features they have a highly tunable set of QoS classes, and they support multiple overlaid virtual networks so that you are able to minimize your jitter and provide excellent performance isolation for different kind of traffic so that small messages are not stuck behind large messages. They also have very good congestion management, and some of their experiments have shown that their network is able to quickly recover from congestion kind of environments, which is typically not the case with other HPC networks. So having said this, note that every network is evolving, and a lot of networks are also aiming to provide similar congestion and quality of service mechanisms. And you might see a lot of these coming up in the future from various vendors. So this is what we have about your basic network adapters. Let's now quickly discuss the smart network adapters. Okay, so Dr. Panda, do you want me to continue?
Yeah. Before that, are there any questions? Let's spend a few minutes. I can share the slides and
Sure.
You can close. Yeah.
Sure. Yeah. My apologies.
Yeah. Any questions?
No, I don't see any questions.
Okay. Can you see my slides?
Not the share screen. I see the slide sorter view.
Yeah. I'm moving there.
Can I ask a question, Dr. Panda and Hari?
Yeah, sure.
Oh, sure, fine.
There were some presentations on nickel and I think Rickel. This is like, we are expected for MPI jobs, the latencies to be around at the microsecond level. But when we are moving to GPU, the latencies are becoming higher. So do you think that these trends will continue? And as a result, in order to improve the performance, we have to rely on bandwidth?
So
go ahead, Hari. Go ahead.
No, please go.
No, so the latency, I mean, how are you measuring it? Is like with a blocking call, non-blocking call, there are all these different MPI primitives are there. So are you measuring it at the MPI layer or a nickel layer or Rickel layer?
I meant nickel versus like MPI latencies, like for instance, using OSU microbenchmark.
Yeah. So multiple things are happening here. So I think Hari introduced that CUDA-aware MPI or GPU Direct RDMA. So at least MRP's library and I believe OpenMPI and many other MPI libraries have that CUDA MPI, CUDA-aware MPI. So you should use that feature first at least, so that you will see very good latency. I mean, we have seen actually on the x86 platforms, GPU to GPU is like a 2 microsecond across the node. So the latency is not that bad. The other thing I think, especially from if you go into the machine learning aspect, like a deep learning, there are multiple solutions out there. And in fact, we have an afternoon tutorial today. We'll go into much more details on that. Starts at 2 o'clock Pacific and 5 o'clock Eastern. So many many deep learning or AI workload are currently, let's say, NVIDIA GPU, they're using nickel. AMD GPUs, they are using nickel. What we have actually done is a tight integration with MPI library. So because MPI library also supports all those collectives, all to all reduce and all, both CPU side and GPU side. So in fact, through that, you can actually transparently, we have a project called high DL, high performance DL. We'll go more into that in the afternoon tutorial. And you'll actually get equal or better performance than using nickel or nickel. So we'll go through that later on. Does that help, Sayan? Or
Q.
okay. Any other questions?
There are a couple of questions on chat. I am posting a response to them. Please continue.
Okay. So let's move to the next section. So we saw that like these are the regular networks. We introduced the RDMA up to some kind of an intelligence, but now actually the field is moving into kind of a smart NIC, and that's what we'll be talking here. And so we'll typically go through like an overview of the smart NIC architecture, NVIDIA Bluefield DPUs, then AMD Pensando, and also the Intel Columbiaville IPUs. Let me see my pointer. I'll yeah. So the broadly two types of smart NICs you will see. Again, there is a little bit of multiple terminologies are being floating around, smart NIC, super NIC, a lot of terminologies, but let's keep that aside. We'll just get the basic concepts here. So broadly two types of smart NICs. So one is like a CPU based kind of we have the NIC, programmable CPU cores, and then ASICs. So this is where actually the NVIDIA this DPU data processing units fall in. Marvell has this Octeon, AMD has the Pensando. And the other approach is to use a field programmable or FPGA based. Okay, so you can use NIC plus FPGAs. So this is where AMD Albio and then Intel's FPGA with smart NICs happen. So now let's take a look at the architecture. So this is a Bluefield 3 DPU architecture. So you remember I introduced this executive assistant paradigm. Okay, so that time we are just talking like let's say one CPU core and one NIC. But in a real system, if you see like let's say this is our server, might be 128 cores are there. Then this is an InfiniBand Bluefield adapter. Of course, it has the RDMA engine, what was there earlier. But now in addition to that, it has a set of programmable ARM cores. Okay, and depending on the adapter, they're trying to adjust the number of cores. So in the Bluefield 3 DPU, you will see 16 ARM cores. And obviously the speeds are different. These are the ARM cores. So here the way I can indicate and you can evaluate it is like a multiple executives and multiple assistants. Okay, or you can think of the assistants are available as a group. So if you have a set of managers, some assistant and secretaries are helping all of them. Okay, instead of having a dedicated one, so there's a shared pool of assistants. So now the question is, how do we take advantage of that? Okay, so just like in a day-to-day world, I mean, if we can offload certain things to achieve some good overlap of computation with communication, then it will be more effective. So here, what we have been exploring. We have a library called MHAPS2 DPU library. This is being done jointly with a startup called Xscale Solutions. So what we have done, some of you might be familiar with MPI non-blocking collectives. Okay, so MPI standard has blocking collectives, non-blocking collectives. So in the blocking collectives, when you initiate operation, let's say you are trying to do an all-to-all, since it is a blocking, unless the operation finishes, you cannot proceed. Whereas the non-blocking collectives was introduced in the sense you can actually introduce your collectives. While the collectives are happening, the processors can actually proceed and perform the next step of the computation, which is not dependent on that data. Okay. And if we can do that at an application level, it has actually good overlap of computation and communication. And that's what also happens many times in our day-to-day world with an executive assistant paradigm. The executives may say, yeah, send out these emails or make a phone call or set up a Zoom, but the executives are not sitting idle. They are continuing to do their work. So that is the kind of paradigm we first started putting it here. So what we have done, we have actually offloaded MPII all to all, MPII Bcast. Gradually, we are offloading scatter, other kind of operations. So that is actually an ideal situation because you can think of the ARM cores. I initiate an all to all, and while the ARM cores are actually trying to take care of the all to all, the application can proceed. Okay. Of course, you need to make sure that that application supports non-blocking operations. And what we have done here, the some end results I'm trying to show, there are very detailed results we presented earlier at GTC and all. You can take a look. We took two things we did here. So first, like this is the MRPs 2. That's the basic MRPs library, which doesn't have any offload. The other one is the MRPs 2 DPU. That is the optimized version where MPI I all to all has been uploaded, or IBcast. All these collectives, non-breaking collectives have been uploaded. At the same time, we modified a P3D FFT application. This is a P3D FFT, just like a representative of FFT application. It has all to all, but this has a version of I all to all. Okay. So that means the processors actually perform some computation and initiate non-blocking all to all. And while that operation is going on, you can actually perform other computations. So we put this on top of our MHAPs to DPU, and this is how the numbers come. So these have been taken like a, think of 16 nodes, 32 ppn, like a 512 core configuration with different grid sizes. We are operating on different like application size. And the overall y-axis is latency. That means lower is better. And as you can see, on a 512 cores, we are able to improve at a P3D50, like a semi-application layer or a kernel layer. You can think of like a 17 to around 16, 17%. Okay, so that really shows like you can actually use, just like in the real world, you can overlap computation communication. The same thing you can do it here. This is another application. So what we have done is the same MRPs to DPU, but we accelerate the HPL. As you know, HPL is the high performance link pack that actually uses non-blocking Bcast. And this is a CPU-based HPL, just to clarify. And then that modified version is available also as a separate package, Xscale HPL DPU. And now if you put them all together, you will see for different process grids and all, add an HPL, CPU-based HPL, we can actually boost the performance. Here it's a higher is better, around like a 18%, 15% kind of things, depending on your problem size. Okay. So then this is another application. This is a X Compact 3D that is from UK. So here again, we modified that application because here, just like think of executive assistant paradigm, let's say you are a manager, you didn't have any secretary to work with, and your upper level management is very happy with your progress, and they say, oh, now onward you can have a secretary. You will be very happy. I mean, right? But you need to modify your workload or your workflow. Okay. Unless you decide saying, oh, I have a secretary, but everything I'll do, then that doesn't help. So you need to create your workflow saying, okay, what you can offload to your secretary so that you can do other things. Okay. So to take advantage of some of this DPU functionality, at least in this paradigm where we are trying to offload the MPI, non-blocking operations, other operations we'll see in the next slides, you may need to modify the workflow. And that's what we did here. The same thing, X compared 3D, we are able to get like a 7 to 10% benefit here. So those are the collectives. Then we offloaded the point-to-point, okay, and also reduction. So MPI like a MPI I send, MPI I receive. And the way we have done the study is with PETC. Some of you might be familiar with PETC. So PETC is it solves 3D Laplacian 27-point finite difference stencil. It's a very big application suite which gets used in a lot of applications, even using OpenFOAM and all. So we try to go inside and then trying to see the main kernel. Can we actually modify the solver algorithms to efficiently offload reduction? And here we also offloaded some part of computation, okay, in addition to communication. I need to be a little bit careful here because these ARM cores are not very heavy weighted. So you need to a little bit balance it out, saying, okay, how much I can offload in terms of the actual application computation. If you offload too much, it will be very slow. Okay. So with an ideal, like an experimentation here, we can see like up to an eight node experiments here, problem size 256, 256, 256, it is a strong scaling. So we are able to give you like a 18% to 24%. Okay. So like this, a lot of solutions are available from these Excel solutions. So if you have any interest in these kind of solutions being deployed on your system, please contact us. The other things what we have done is a similar AI workload. Okay. And these are like a CPU based training. So we have just started first with a CPU, DPU. We are moving into GPU, DPU. In the end, you will see modern systems will have CPU, GPU, and DPU or IPU. So one has to redesign this middleware for all these kind of components in mind. But currently, we have CPU, DPU solutions here. So this is the accelerating CPU-based DNN support. So we have, like as I was telling earlier, so we have done this high performance DL where we have you can run actually distributed PyTorch, TensorFlow just directly on MPI. You don't have to go through Nickel or Nickel, any of those, and with a Horo board and with a modification. And here we support like a PyTorch framework for deep learning. And this is how it looks like. This is a training of ResNet 20B1 model on CFAR data 10 days set on the Bluefield 3 up to 16 nodes. And here is the time per epoch. So the lower is better. And here we are able to show like around like a, depending on the number of nodes and all, almost like an 18% overhead. Okay. So we also have worked on more. We didn't include here because we have limited time. Think of like other operations like IO, checkpoint restart. All those kind of operations, actually the DPU technology is ideal. So then you should be able to offload to those. So then the other architecture, just to provide an overview. So these like the AMD SmartNICs. So this is the AMD Pensando, and this is the Alveo kind of things. These are again follow very similar kind of things. We have not experimented with any of these, but the same ideas or concepts can actually follow here. And Intel is also working on very similar things, what they call it Intel Infrastructure Processing Units or IPUs. And they also have the Intel FPGA-based SmartNICs. So it gives some kind of a high-level overview. If you go here, this is like the Intel FPGA SmartNICs. They have the 200 gigabits per second Ethernet. They have an onboard Ethernet controller and the Intel Agilex FPGAs. And this is the Intel IPU, which has already like a packet processing engines, RDMA storage capabilities. Also, they have a set of ARM cores. So all these architectures, like whether it is AMD or NVIDIA or Intel, even Octeon, they're almost going in a very similar direction. Each one has different features. But the main challenge is like, how do you design the upper level software stacks? Okay. At least here in the context of what we are discussing, there are also communities are also trying to offload other things like a virtualization. For example, the cloud might be some security procedure, some encryption. So I think over the next several years, we'll see gradually this side, more and more intelligent adapters will be coming up, and it opens up many challenges to see how to redesign the upper level middleware. Also might be some co-design with the applications so you can boost the application performance and scalability. Any questions here on this part?
There were a couple of questions on chat and on Slack. I have addressed those. I don't see any additional questions.
Okay. So if there are no questions, let's take a look at a little bit of the next section. Might be Hari, you want to cover this?
Yes. If you can stop the share.
Yeah, I'll stop share. So
thank you. So we started with basic the fundamentals of high performance networking, basic high performance networks, smart networks, and now we are heading into how AI based network deployments are happening. So we'll take a couple of specific use cases, the Cerebras and the Habana Gaudi. So more recently, you would have seen that Cerebras has released a wafer scale engine or WSC3 architecture with over 4 trillion 5 nanometer transistors, a heck of a lot of AI cores, huge amount of performance, a lot of memory, and a very rich network. So for you to get a scale of how the GPU compares to the wafer scale engine, This is how it looks like. So as you can see, it's a really, really, really big chip. Okay. So this is a comparison of WS3 with NVIDIA H100. All of this is courtesy of Cerebras, nothing that we have come up with. So they have significantly higher performance, as you can see, from the compute side, the core side, memory side, or the communication side. So with all of these, we see that Cerebras is able to give very good linear scaling. So until about a year ago, most of the Cerebras compute systems with CS1 was limited to mostly one box. But with CS2 and more recently CS3, we see that Cerebras is trying to put together larger clusters, multi-node clusters, so that you are efficiently able to scale out deep learning training, particularly large language model training. And the goal is that you have significant ease of use. So just by modifying some small numbers in your input YAML file, you're able to scale out in a very, very easy fashion. So that is the goal with Cerebras. So there's a question from Ram. Is there any work similar to CUDA-aware MPI for topology-aware MPI, particularly for optimized Dragonfly topology? Yes, we do. We have done some work. In fact, my thesis was on topology-aware MPI for a factory and other clusters. There is work by a lot of others in the community for topology-aware communication. If you remember IBM, when they had their blue gene systems, they always used to have topology-aware communication algorithms. So there are a lot of solutions in the community by various people, including us. So getting back to Cerebras, so this is how they're able to scale out. So we can see that they are able to achieve very near linear scaling. The other AI architecture that we are going to look at will be the Habana Gaudi. So this was a separate company which Intel acquired for a couple of $1 billion several years ago. One major difference between Habana and other architectures is that they have the network on the chip itself. So you don't have to go out of the chip to reach the network. So they have a bunch of tensor processing cores, a lot of on-chip memory, and RDMA or Converged Ethernet V2, Rocky V2 chips, engines on the chip itself. So using this, you are able to interconnect a lot of these Habana Gaudi chips with a rich intranode or internode interconnect. If you look at the Voyager system at the San Diego Supercomputing Center, that is one such system with a lot of these Habana chips, particularly meant for AI training. So just like Nickel had Nickel, NVIDIA had Nickel, AMD had Rickel, Habana has their own collective communication library called HICL or HCCL. We at the Network-Based Computing Lab had added support for HICL inside the MVAPICH communication runtime. So MVAPICH has unified support for Nickel, Rickel, HICL, whatever you want to, so that you get the best performance that any communication runtime is able to offer out there. And with such solutions, Habana Gaudi's team has able to show that they are able to get very good throughput for various large language models as seen in this graph. So again, no offense to any of the DL vendors or chip vendors out there, but just because of the lack of time, you're only able to show two of these solutions here. This by no means is the gamut of GPU vendors out there. So you have Samba Nova, you have GraphCore, you have several other vendors out there with Grok is another GPU vendor. Not GPU, AI vendor out there. So this is just a couple of things that we have been able to highlight so far. So with this, I'll hand it over to Dr. Panda to provide an overview of software stacks for commodity high performance networks. In the meantime, if you guys have any questions, I'll be more than happy to take them.
Okay, thanks, Hari. Let me open up. Okay, you can see my slides. Hari, others, can you see?
Yes, I can see the
Yeah.
slides.
Okay. Good.
Yes.
Thank you. So let's take a look at, we saw all these different networking and also what we'll try to do now in the next section, we'll take a look at a little bit of software stacks, how things have been evolving, and then we'll take a look at some sample case studies, performance numbers to get a feel, and then we'll conclude. We have around 30 more minutes to go. So when this field started, um, in the very beginning, of course, we have the hardware. Since InfiniBand was an open standard, there was a lot of initiative. I'm just going back here, like almost early 2000, a lot of DOE labs. There were multiple vendors of InfiniBand. There was an organization called OpenIB. And then so the idea was that these adapters will be there, but then the software stack will be developed just like with following the Linux model. And people can actually, the vendors can contribute a driver, both user level and kernel level. And then the upper level, the entire stack, including WinMPI, all the other software stacks, so that the people can actually download these stacks and then deploy it on the system. So it actually, that was a very nice model. It started. Then when iWork came from Chelsea, there was a lot of discussion. Net Effect also, there was another company. So then there was a lot of discussion, and then this IB community and then the iWork community merged together, and then the Open IB was renamed as Open Fabrics. Okay. And so the objective was, again, as I said, to incorporate IB, Rocky, iWork in a unified manner, support for Linux as well as Windows. So including us, many other organizations participated in that effort. That actually was very successful. It continued for many years. And that actually led to something some of you might have heard of called OFED, or Open Fabrics Enterprise Distribution. So these were all being tested together. So as an end user, if you're just deploying a cluster, you put together your hardware and you just deploy the OFED stack and things are ready. Even you have MPI libraries, multiple of these, you can actually run your applications and all. So it evolved over the years, but then actually there was some friction started within the organization, just like any other organization. The latest version went into OFED 5.3. So 5.2 was released, 5.3 was being developed. Um, what happened between this OFED, there was a little bit of branch happened. Some of you might have heard of called MOFED. So that was the Mellanox version of OFED. So that time Mellanox, they kept on adding some new features which were not being incorporated to the OFED. So they developed a separate of their Mellanox OFED with their own features. So it got fragmented. And then there was a very big conflicts. Here again, I'm just telling the fact. I mean, some of you might be from these companies. There was some friction between NVIDIA / Mellanox. That time it was Mellanox and then Intel. So now, if we move forward, there actually it has been bifurcated. The community has been bifurcated. One is a UCX consortium, then another one is a Leaf Fabrics or Open Fabrics consortium. So these two are there. So UCX, it is like this is just trying to show like a timeline kind of things. Again, overall, over the years, they have been putting together all these different components, the protocols, the mid layer, then the upper level stacks and all. So they have the UCX, UCC, OpenSnappy, even some Spark, UCD. So they have all these components for a complete stack. And this is heavily optimized for Mellanox InfiniBand. Okay. You can also support Rocky here. But other network like Slingshot and all, you cannot do. There is a port out there. People have contributed, but not. The other community, which has been led by Intel, mostly it is called Leaf Fabrics, or it is a part of like a Open Fabrics interface. So in fact, annually you will see there are two events. One UCX events happens in December. There is an OFI events happens in, I think, March, kind of a time frame. So these two communities are evolving. So this Open Fabrics or a Open Fabrics has the lower level called Leaf Fabrics. And this is what they have defined as like a Open Fabrics interface. So the idea is very similar, but a little bit different. So here the idea is that every time you design a hardware, the Wi-Fi provider can actually provide some of these APIs. And using the Wi-Fi interface, you can actually query or do callback function and implement the upper level thing. So the idea is that below can be opaque. So you may not be knowing anything what is happening below, but as long as you are following the Wi-Fi interface, then you should be able to design. So in fact, this is like, for example, I'll introduce later on MHAPI's project. Some of you might be familiar. That is the project in my group. We have been doing it for 23 years. Earlier, we were doing like a direct burst interface. So through that, we were able to support IB, Omnipath, Rocky, IWAR, many of the interconnects. But then when Slingshot came, Slingshot only exposed it through Wi-Fi. So in the beginning, we were not able to support. But since last year, we have actually our MAPH moved to 3.0 and 4.0 series. So there actually we support both Wi-Fi and UCX. So through those support, you will be able to actually uh, use any interconnect. So now we are able to support all the interconnects. In fact, very latest Wi-Fi 4.0, we even brought back our own InfiniBand VERFs level support. So we have a lot of flexibility now for different interconnects. And then while we were talking, I think there was a question came earlier and it was mentioned there is another consortium which is getting momentum. This is called Ultra Ethernet Consortium. So this is where I think all the Slingshot, HP, Broadcom, and many other companies, Intel and all are joining the effort to see it will be pure Ethernet. So there has been a lot of, I think you saw some earlier slide how he presented. Earlier, there was a little bit of gap in performance between InfiniBand and Ethernet. So that's why all these intermediate protocols like SDP were introduced. But over the years, especially after the Frontier system was deployed, that was like HP's with Slingshot interconnect, and the Slingshot actually gives the APIs more like an Ethernet. Um, so this debate is still continuing. It is not completely resolved, uh, but these Ethernet companies are putting it together, are working together to bring it to the Ultra Ethernet Consortium. And the idea is very similar. Again, Ethernet physical layer, link layer, IP layer, and the transport layer. And this is the software all the different collectives like Nickel, Rickel, MPI, OpenSPAM are being put together, and then the applications. So as long as you are following any of these things, UCX or Wi-Fi for the time being, or if you are on the Ultra Ethernet Consortium, you will be seeing software stacks will be coming, and you will be able to directly utilize those. So with that, let's take a global picture of where this field is. As I said, many of you must be familiar with the top 500. And these are some of the numbers. If you go to the top 500, you yourself will be able to get these kind of charts. It shows over the years what is happening to, like, this is a InfiniBand, this is Ethernet. They have a little bit of misnomer. They call like a gigabit Ethernet. Ethernet, these like the some of the other networks like the custom interconnects. So some of you might have seen these kind of pictures from the top 500. You can also download these. So typically there is a fraction distribution in terms of count, and then the other one is terms of performance. So the count is very simple. Out of 500, which one belongs where? So here it's, let's say InfiniBand is 48%, Gigabit Ethernet is 39%, others are here. In terms of performance, so this is like a, if you combine the performance of all 500 systems, then you say, okay, how much InfiniBand-based systems are contributing, or how much Ethernet-based systems are contributing. So here, if you see, in fact, Ethernet, since this number one system, which is the exaflop system, Frontier, that actually contributes a big weightage on the Ethernet side in terms of the performance. The single system dwarfing a lot of other systems. So here you will see these kind of distributions. If you go down a little bit, these are all from the latest June 2024 list, which was announced at ISC. We'll see a new list in another 4 months, I think 3 months in November. So currently there are like a 43% of the top 500 systems are InfiniBand. Starting, this is the largest one, which is the number 3, almost like a 1.1 million core. Microsoft, Seneca, Mayer Nostrum, then Oak Ridge, which used to be number 1 at some time, has gone down. On the Ethernet side, this actually combines all the different kinds of systems. In 10 gig, 25 gig, 50 gig, 100 gig, 200 gig. Of course, as I said, Slingshot 11 at the number 1. That is the number 1. The number 2 is actually Aurora system. That is also an exascale system. So these are, as you can see, like 8.6 million core, 4.7 million cores. They're much more bigger than many of these other systems. And in the latest release, there have been a lot of these new layers have come out. So you will, this gives a perspective of where things stand, and of course we'll see this continuously gets evolved over the years. Any questions here from anybody? Okay.
No, I don't think there are any questions.
Okay, thanks. So then let's move to the kind of a sample case studies. So here what we'll do is just to give you a feel. We talked about a lot of concepts, but if you really take the latest systems, where do you think these are some like a basic experimental number? These are all taken within my lab. So these are all reproducible. These are also we'll see based on the like the OMB or low level latency. So we'll see low level performance and then the MPI. So this is what like you can think of. We talked a lot about uh, um, Infiniman and Rocky. Um, so here these numbers are taken a little bit older hardware like ConnectX-4, EDR, and they are connected back to back. But the idea gets clear. So the whole idea is like this is a network layer. We are not bringing any of the upper middle layer. So here you will see like let's say the Infiniman provides 730 nanoseconds. Okay. So like from a node to node, when I say node to node, that is like a memory to adapter to link or switch. This is not a switch, so it's back to back adapter and then memory. The Rocky has a little bit of overhead. Okay. So it is around like 130 nanosecond overhead on top of the Infiniman. If we take a look at the bandwidth, which is like a unidirectional bandwidth, they come very close. There is like a IB goes a little bit higher compared to the Rocky, and it again sometimes also may change based on the kind of switches you are connecting. The Rocky, as you know, is RDMA over conversion on Ethernet, so you can actually use any of the Ethernet switches. You can use from Broadcom, Arista, even Mellanox also slash NVIDIA. They also sell Rocky. So in fact, from NVIDIA slash Mellanox, the adapter is exactly the same. Okay, with some minor differences, so that the similar logic, which is trying to accelerate the Infiniman as well as for Rocky, only the some of the firmwares and all are modified so that you can use the Rocky interface. Now, if you go into a little bit of like a differentiation or evaluation between sockets, we talked about these R sockets and IB bars. You will see very clear differences. So this is like the sockets. This was again at the ConnectX EDR, that platform. Here you will see like around like a 6 microsecond at the TCP versus very close to like a 1 microsecond at the Infinity R sockets or IB bars. And here you can see actually the R socket, that's how it was designed, that um, you don't have to go through all the complexity of InfiniBand, but still be able to give very good interface to the upper layer, especially with TCP/IP traffic. In terms of latency, you will be able to get good performance. In terms of bandwidth, R sockets has a little bit of issue in the driver during that time at the middle messages. But if you go very large messages, Infiniman and R sockets were able to deliver very similar performance. But the TCP/IP doesn't deliver that much because of the higher overhead associated with this. And then this is how you see a gap. Now we talked about this AWS EFA adapter. Hari mentioned to this. Their design philosophy is a little bit different with respect to their data center, how they are operating the AWS cloud. For them, their workload, latency is not very important. So that's why you will see if you do some basic performance here, it is a UD based that we talked about, the scalable reliable datagram SRD based. Here you will see like this is a high overhead compared to InfiniBand. When we are talking about 1 microsecond latency and all InfiniBand, here it is around 16 microsecond latency, but it is by design. They are doing this because they have the different philosophy of spraying the network, giving different kinds of providing different kinds of congestion management and all. And here it is trying to show like some kind of performance difference between UD and SRD. SRD typically adds some additional overhead compared to UD. This is the Broadcom. They have been working on Rocky adapters. So this is some evaluation on their net extreme SCA 100 gig. Now they have a 200 gig adapter. So these numbers here you can see it comes to our latency is around 3.37 microsecond. The bandwidth effectively you get like saturate the like a 12. If you do a multiplication here, you will see like a 12.5 you should be getting for 100 gig. It comes very close. So again, I just want to indicate these are some sample numbers. Um, if of course the technology is changing very fast, so if you are looking for the numbers, you should actually do it yourself, so that you will see based on the what CPU, what GPU, or the network adapter and all, the performance will change little bit, uh, but the trends maybe will almost remain the same. Okay, that's what I just want to indicate. So then next, if we go into one upper layer, like here, we'll just take MPI. This is the project I was talking about. Many of you might be familiar. This is called the MHAPPIS project. We started this project almost the day one of InfiniBand. Prior to InfiniBand, we were working on Quadrix, Mirinet. Some of you old timers might be knowing those technologies. When InfiniBand came, even though hardware was there was no ecosystem for software. So we were the very first one in my group in the world to jump in and have the MPI running over InfiniBand. And in fact, we gave a demonstration uh, almost 22 years back at Supercomputing O2 um, over InfiniBand. And since then, we have MIP's project has been continuing steadily. I'm very proud of my team. We are able to, while being in academia, we are able to run, develop production quality code, deliver it to the community, and sustain it for 23 years. As many of you know, there is a lot of discussion going on sustainability in the community. Purely from a software development, we are able to maintain that with all different kinds of funding. So currently it's being used by more than 3,400 organizations. These are registered organizations, excuse me, in 92 countries. So if you go to this MWAP side, we have actually a user tab. You should be able to exactly see how their people are using. We have also crossed, like just from our OSU site, we have crossed like a 1.8 million downloads just from our website. Of course, it is a part of all the different stacks like Red Hat, SUSE, OpenHPC, SPAC. It's very hard to keep track of those, but just from our website, we can keep a track, and we are going very nicely there. But in addition, we are actually over the last 20 years, we have been working with this community, networking community, the systems community, top 500 community to make sure that even our MIP stack is also empowering many other top 500 clusters. So here, there are some examples here. So if you take a look at it here, these are some of the sample numbers just to show over the years what has happened, just to understand the trend. Here it says like a starting with a true scale QDR, FDR, dual FDR, EDR. This is SDR. And then the omnipath, and these are all the details like on the what systems they were taken, mostly the similar systems. So the message I want to give, the left hand side is like a latency uh, and message size, and the right hand side is latency for large message size. Okay. So for small messages, mostly you will see they are hovering around 1 microsecond, 1 microsecond, 0.9, different vendor, different adapters, servers, you will see around in that region. And once you go to the large messages, of course, the bandwidth makes a big impact. Okay, so whichever network, like as you can see, this latency is reducing over the years. As you have the network higher bandwidth, large message will improve. Now here we are trying to show the bandwidth. This is the unidirectional bandwidth and bidirectional bandwidth across message size. So this is this is the million bytes per second. There is a little bit of conversion. These are all taken with the OSU micro benchmark. That is also a part of the MAPIS project. That is open source. Many of you must be familiar. That is also kind of it has become like an industry standard. For any networks papers, you will see even a lot of procurement. You will see some bullets saying, okay, please refer using OMB numbers. So that is from my group. That's what we are using. So you should be able to also utilize the same thing to get these numbers. And very nicely, you will see like this stepwise curve. Like over the years, the bandwidth is improving, and similarly also bidirectional bandwidth is improving. If we take a look at the Rocky adapter earlier we saw at the lower level, this is like a one level up. So you can see that, for example, this was like a IB was 730 nanoseconds, and this is like a 991. So we are able to like a what 140 nanosecond is kind of a MPI is providing the overhead, okay, on top of the network, just to give you a ballpark. So these are very low overhead stacks we have designed, and this is where you use very extensively all those RDMA operations and exploit all the different VARs. Of course, this is a one-way latency using blocking send and receive with non-blocking collectives and all. There are a lot of numbers are out there. We'll not have time to go over all those things. This is the same thing, but in the bandwidth, it follows a very similar trend, just like what we saw at the lower level. So the Infiniman and Rocky are able to give more or less similar bandwidth. It is a little bit higher. The Infiniman, there was a question here, am I right?
So
Let me.
the question is, would you happen to have this curves charts but plotting on an orthogonal axis with respect to the number of processes involved for a... Yes, we do have charts for collectives, but not on these slides. If you go to the MVAPICH website under performance, we have a detailed set of numbers there.
Yeah. So these are just, we are showing point-to-point numbers. Okay. So similarly, we have a lot of collective numbers. As Hari said, please refer to our website. Or if you have an access to any of your systems, you can actually run the OISU micro benchmarks. Those benchmarks, it has not only point-to-point, it also has a collectives. Okay, so you should be able to see. So this is the Slingshot 11, like the frontier, as I said, like starting from our 3.0 version, we are able to support. And then this gives around 2 microsecond latency point to point, and we are able to almost go into like a similar like a 200 gigabits per second bandwidth unidirectional on the Slingshot network. If you take a look at this is the OPX we talked about, Omnipath, and then the kernel-less network has the Open Fabrics, the OPX, and that again has multiple lower layers, like either you go to the OFI or you can do PSM. There are different options. So at an MPI level, actually OPX is competing with almost Infiniman. It's around like a one microsecond. In some of the platforms, actually, we also shown like a lower than 1 microsecond, around 0.91 or 0.92. It all depends on, again, the system configuration, as I was telling, depending on the processor speed. You may see some difference because some part of the calls are still being done by the processor. Right? So, and then this is on the Broadcom Rocky. Here also we see very similar kind of things I showed earlier. This has a little bit more of the bandwidth numbers. Here we are able to go into like a 100 gigabits per second, and bidirectionally is very close to 200 gigabits per second. We have not done the Thor 2. We did a little bit of earlier things on their system. I believe they are still tuning some of their drivers. And once we do that, we'll be very happy to even share their Thor 2 adapter numbers. So with this, we'd like to conclude here. Just again, this just gives a very sample. That's what I tell. I mean, there are so many different performance numbers. Even at the Hot Interconnect conference in the earlier years, we have presented many papers. Please feel free to take a look at those so that you can get an overall idea. Are there any additional questions before I put a concluding remarks?
No, I think that's it.
Okay. So at a high level, if you see, like we almost talked very little bit more than 2.5 hours. We started with a very high level perspective, high level objectives and goals of this high performance networking. What is the requirement? We looked at the history, what has happened, and gradually we are seeing that more and more intelligence are coming to the adapters, to the to the switches, and we also talked about some of the smart networking architecture, the trends, highlighted the main features, gave an overview of the high performance network hardware software ecosystems, discuss some of the sample performance numbers. But as we see the trend, you will see more and more because systems are becoming denser. I indicated more and more GPUs are coming together. Um, Server density is increasing, and to have the good balance of computation and communication, and to deliver very good performance in scalability, both strong scaling, weak scaling for HPC and AI application, people are exploring many of these smart networking architectures. Whether you make the basic hardware, basic adapter much more faster, or put intelligence in the adapter, or put intelligence in the NIC. But as these are being added, the software ecosystem is also evolving. Okay, so that leads to a lot of innovations. Every time a new adapter comes, it just opens up avenues, and unless you actually bring that software ecosystem ready, you don't see that people trying to adopt that. And that's what actually from our group, we are been working in this area for almost last 30 years, and we try to bring all these latest results to all of you. I'd like to thank all our sponsors, funding, equipment donation, and that's how we are able to share this information with all of you. But more importantly, these are all my heroes. What we presented is like a 2.5 hours, is actually a work by almost 100 students over the last 20 years. Many of these names might look familiar. They have graduated from here and are holding positions in many other companies, NASA labs, academia kind of things. So I would like to thank all of them. So every time I present these things, I'd like to salute them. So with this, like to close. Our email addresses are here. If you have any questions, please feel free to send us a note to myself or Professor Subramoni. And as I said, we have another tutorial today in the afternoon at 2 p.m. Pacific, 5 p.m. So there we'll be mostly focusing on the high performance training, inferencing, and see how these high performance networks can actually you can take advantage of that and how that field is evolving. Okay. So with this, I'd like to thank all of you. If there are any quick questions, we can take care now. You can post it in the chat, or we can talk.
The tutorial in the afternoon at 2 o'clock or 3 o'clock?
I think it is 2 o'clock. Am I right? Please
Give me
take a
a
look.
second.
This is on the track 2. There are 2 tracks. I think track 2, there is a.
So our tutorial begins at 2 o'clock Pacific, 5 o'clock Eastern.
Eastern, yes.
This is the principles and practice of a scalable and distributed
Yes.
deep. Got it.
Yes. It begins at, so this is the link to the tutorial. I am posting it in chat or on Zoom here. So that is the direct link on the Hot Eye program. So it is August 23rd, 2 p.m. to 5 p.m. Pacific time.
Yes.
The slides for this other tutorial, where is it available? How I can get it?
Which
so
one?
The slides for the tutorial, if you join the tutorial, we'll be providing a link to that. So I hope that helps.
Okay.
Yeah, the slides for this tutorial are available. We posted that earlier.
Yes, okay. I see that. Thank you.
Yeah. So please join the other tutorial. We'll give you a pointer also.
Thank you very much.
Thank you. Bye.
Thank you very much. This was a great tutorial. If you all want to stay on and take questions, you're welcome to. I just wanted to remind everyone that I did put the Slack channel for this tutorial in the chat, and that will remain open after the tutorial ends. So just so that everyone's aware, that is so open.
Thank you. Thank you, Amanda.
Yeah.
See you later. Bye.
Yes, thank you. There is a 15-minute break as well, and we will start the next tutorial at 12.
Yeah.
Sorry, 12 Mountain at 11 Pacific.
Yes.
Thank you.